Here are two different arithmetic sequences. They begin with the same number, but the difference between adjacent numbers in the top sequence is different from the difference between adjacent numbers in the bottom sequence. Hopefully in the top sequence you can see that the numbers are increasing by 3, and that in the bottom sequence the numbers are increasing by 5. The position of each number in the sequence is referred to as a term. The first number is the first term, second number is the second term, third number, third term, and so on. The value of each term in the sequence is given by the expression a sub n, or small n, where n represents the position of the number in the sequence. If we focus on the top sequence, we can see how each term in the sequence is expressed using that system. A1 is the value of the number at the first position, A2 is the value of the number at the second position, A3 is the value of the number at the third position, etc. I've added 3 dots at the end of each of these sequences because the terms can go on forever. Because these sequences are so large, if I ask you to find a term with a very large number, say the 2000th term, you'd be writing this list out forever just to find out what that term is. And that's why there's a formula for finding the value of any term in this sequence, no matter how far along the term is in the sequence. It could be the 1000th term, the millionth term, we can still find its value. There is more than one formula, but I'm going to focus on a specific one. We're going to examine this expression and I'm going to show you an easy way of understanding how it works. Now let's just do a quick overview of the equation. Remember we said that an represents a specific term in the sequence where n is a position. So an, which is the value at the position, equals a1, we know what that is, that's the first number in the sequence. And then we add another value to that, which is the position number minus 1 multiplied by the common difference between each number. And the common difference between each number for this sequence we saw earlier, and I'll show that again, it's 3. So just as an example, if I ask you to find the value of the fifth term, the position number we're looking for is 5, and so we'd be looking for the value of a5. That would be equal to a1, well a1 is 2, plus brackets n minus 1, well that's 5 minus 1, multiplied by the difference, which is 3, and that equals 2 plus 4, 5 minus 1 is 4, times 3, which is 12, plus 2 is 14, so at position A5 we should have 14, and you can see that's exactly what we have. So let's try to figure out exactly what's going on here and why these expressions work. So let's examine the elements on the right hand side of this equation. The first element is a sub 1. It's called sub simply because it's a small character attached to the main character. And because it's given the fixed value 1, it always refers to the same position in the sequence, which is the position of the first number, which is 2 for this particular sequence. The second part of the formula is a multiplication of two elements. The d is the difference between adjacent elements in the sequence. You can also think of d as a number that you add to an element in the sequence in order to get the value of the following number. For example, in order to find the number that follows 20, we would add the difference, which is 3, and that would give us 23. In the formula, d is multiplied by n minus 1. But what does this n minus 1 do? Well, consider how you'd go about finding the value of an element that's in a certain position in the sequence. You'd go from position a sub 1, which is the first number in the sequence, and keep adding the difference until you get to the position whose value you're trying to work out. So for example, if I wanted to work out the value of the element at the third position, that is the element at a sub 3, so n equals 3, but how many times do we have to add the difference in order to get to the third position? Well, we had to add the difference 2 times. So to get the value at a sub 3, we started at a sub 1, and we added the difference 2 times, and that gave us a1 plus 2 times the difference. But 2 is 3 minus 1, and 3 minus 1 is really just n minus 1. So this can be rewritten as n minus 1 times the difference. So what we really have is a1 plus n minus 1d, and that is just the elements in the formula. So n minus 1 is a number of times you have to add the difference to the first element in order to reach the position of the element whose value you want. One more thing I'd like to point out that makes this formula even easier to understand, and that is that n minus 1d is just one of the numbers in a times table. Because the difference is 3 in this sequence, this will always be one of the numbers in the 3 times table. When n was 3, this was 2 times 3. If n was 4 and we were trying to get the value of the fourth element, we're adding 3 times 3, 9, to the first element, and 9 is part of the 3 times table. If we're going for the sixth element, it's 5 times 3, which is 15, which is part of the 3 times table. Hopefully you have a better understanding of arithmetic sequences. Here's a couple of questions to try. Find the 62nd term in this sequence. So n equals 62, and we're looking for the value of the term a62, and that equals, well, a1 is 2, which is the value of the first term, and then we're adding, well, n is 62, so n minus 1 is 61. That's 61 times d, which is a difference, that's 3. 61 times 3 is 183, and we add 2 to that. 183 plus 2 equals 185. So a62 equals 185, and that's the value of the 62nd term in this sequence. Question 2 is show that 84 is not a term in this sequence. How do we approach this one? Well, in the expression, an is the value of the term at the nth position, and we've been given the value 84, so we can say the value at the nth position is 84, and then we can check to see if there really is a value of n such that a sub n equals 84. So in our equation, an equals 84, so we can write 84, and that equals a1, well, a1 equals 2 plus n minus 1 d, or d equals 3. We can subtract 2 from both sides. That will give us 82 equals n minus 1 times 3. Divide both sides by 3. The 3's on the right hand side will cancel, and so at the moment we have n minus 1 equals 82 over 3. If we add 1 to both sides, we get 82 divided by 3 plus 1 equals n. I'm going to make things a little bit easier on us by calling 1 3 over 3, and that will give us two similar fractions. So 82 over 3 plus 3 over 3 equals n. Now we can add these two together, which gives us 85 over 3. Now I don't think 3 divides 85. And how I'm going to show that is by changing this again. I'm calling it 81 plus 4, and both over 3. 81 over 3 plus 4 over 3 is 85 over 3, and that equals, or 81 over 3 is 27 and 4/3. So n equals 27 and 4/3. So what this is saying is that if 84 is a term in this sequence, then its position would be 27th and 4/3. Well, 27 and 4/3 position doesn't exist. It would either be 27 or 28. You can't have a fraction of a position. And if this position doesn't exist, then 84 is not a term in this sequence. So we've answered the question. Thanks for watching.